Good day to all of you. So today we are going to discuss how exactly we are going to run the statistical analysis that is required for a repeated measures design, a study with repeated measures design. Now, in this semester, we have discussed about the theoretical basis for considering repeated measures designs, and also I have introduced how to apply repeated measures t-test or the dependent t-test, and also the repeated measures ANOVA. Now, what we are going to do today is that we are going to come up with a practical scenario you can see right now on the screen, and I'm going to help you understand how exactly we are going to analyze this data. Now, this is a very simple study, a hypothetical one actually. I just come up with this today morning while I was preparing for this. So here goes the title, Investigating the Effectiveness of CBT in Alleviating Suicidal Ideation. Now, before we go ahead and discuss about how exactly the analysis need to be conducted, let's discuss a little bit about what this study is exactly going to be. Here I have given a very simple description. So let's take a moment to read this. Here it says a research assistant in the XYZ hospital wanted to investigate the effectiveness of CBT. After a discussion with a psychiatrist, I'm going to write he or she, because I don't know who this person is, just hypothetical, recruited a group of 20 patients who were diagnosed with depression. So we have 20 patients now. The 20 patients were identified to have moderate to severe depression, which was measured with a psychometric tool developed by the hospital. So there's a tool, and they have used this tool to assess whether these individuals are suicidal or not, whether they pose any risk or not. So a score of 30 plus indicates severe suicidal ideation, while 20 to 29 indicates moderate, with 19 or below indicating low risk. So obviously, individuals with depression tend to have some risk of suicide or suicidal ideation. They usually do come with such symptoms. So this research, or this data, helps us to see whether CBT, cognitive behavioral therapy, is good at alleviating suicidal ideation or any symptoms or any signs related to potential risk of suicide. So all the 20 patients were instructed to undergo CBT for 7 weeks. They were measured before the treatments, 2 weeks, 4 weeks, 6 weeks, and 8 weeks after the treatments. The suicidal ideation scores are listed below. So of course here now the CBT goes for 7 weeks. They are measured before the start of the treatments, and while the treatments are ongoing, they are measured at 2 weeks, 4 weeks, 6 weeks, and 8 weeks. So now, unlike the between groups design, usually in the between groups design, we have an independent variable in which you can see multiple groups. And when you write that data, usually you can see on the left side we have listed our groups, and on the right side we have displayed our scores. But if you see here, the independent variable here is the type of administration, because it's a CBT, but we have four different types of administration and before the administration of the treatment. So this is my independent variable. I am measuring these individuals in 5 different times, and I have listed their scores in each column. This is the exact way that you are going to use to add the data to your statistical software as well. Different research, different statistical analysis require you to enter data in different methods. So if you can go through the previous videos on between subject designs, you can see how exactly data is being added in those ones. Now this one is repeated measures. So here I have data from before the treatment. As you can see, majority of the patients are pretty depressed, and also they have higher risk of suicide. Only a few has moderate risk, everyone else has severe risk. And this is week 2's data, which means after a week or so of administering CBT. And this is 4 weeks, 6 weeks, and then 8 weeks. You can see compared to before, after 8 weeks, you can see some of the scores have, it displays a noticeable reduction. Here you have 9s and 10s and all of that, but here it's all 30s and mostly 30s, but a few 40 as well. So now, what are we going to do? I am going to help you guys understand how to do a repeated measures t-test. In this repeated measures t-test, I'll be comparing this before and 8 weeks. But if you want, you can compare before and 2 weeks, before and 4 weeks, before and 6 weeks, and so on. But in a repeated measures t-test, you can select only two particular times of measurement. If you need to measure more than 2 instances, then for that you have to go to repeated measures ANOVA. Now, I'm going to show you both today. So let's first start with repeated measures t-test. So let me open Jamovi. You can of course use SPSS for this as well, but I find Jamovi more easier to use, pretty user friendly. It might not have some of the functionality of SPSS, but I still think Jamovi is a pretty good software, and also it's free of charge. So what is there to hate, right? Okay, so I'm loading up my software here. Okay, the software is here. Let me share my screen. Okay, now this is Jamovi. Now, previously I have told you how exactly we are going to enter the data to Jamovi, but I'm going to show it again. Usually, most of the Jamovi would come with these few tabs or these few, buttons: exploration, t-test, ANOVA, regression, and frequencies. So these factors, SEM, J power, these are all added by this modules option. So if you go to this modules option, you can add more analysis and more types of more statistical solutions into your Jamovi software. Now I'm going to just transfer all the data. So here's what I'm going to do. I'm going to just copy and paste all my data from the Word document, excluding the column headers, just the data, just the numbers. I'm going to just copy and paste. So just click on the first button here and then Control V. It will get all copied like this. Now my data is copied, but I want to make sure this data is properly introduced. So now A, B, C, D, E, this is exactly how the variables are named by default. So this is not good. So I'm going to just double click on this A and then it gives me variable information. So I'm going to just write before the treatments, like this. It's always better if you can actually name your variables well. If you don't do that, when you run analysis, it will just give A's and B's and C's or whatever the other way that you are going to use to name these variables. So that is not good. And then it will make you go ahead and do more editing work when you develop your reports and all. That's too much of work. And it's very important that you select what type of a measurement this is. Now, this one is a continuous variable. Why? Because it has only scores. Now, a lot of students ask how exactly we are going to decide what exactly the right measurement type is. I have uploaded a video on measurements in my research methods playlist. It's one of the first videos. Please click and watch that video so that you can understand how to select the right measurement type. Now, B is actually 2 weeks. 2 weeks after the treatment. And once again, I'm going to make this continuous. Now that is clear. Now let's do the same for C, 4 weeks after the treatment. And again, I'm going to change this to continuous. Now let's go with D, that is 6 weeks after the treatment. Continuous. And this one is 8 weeks after the treatment. Okay, now I think everything looks phenomenal. Okay. Now, see, this is pretty easy. Now we have added all our data. Now, compared to an ANOVA, running a t-test is very straightforward. So click on this t-test right here, and it pretty much gives you most of the descriptives in this arena itself. So it's pretty straightforward here. So now this is not independent samples t-test or one sample t-test, this is paired sample t-test. We are going to go with that. Now, you can select, now here we have 5 different instances of measurement. I want to see whether before the treatment and final week of assessment has a clear, noticeable, what do you call, significance in terms of their score difference. Because the higher the score difference, the greater I can, the greater the effectiveness of CBT is, assuming everything else is held constant. So how to keep things in constant and all of that, that is part of the research methods. But I am going to just focus on the statistical analysis here to see how different these the average scores of the 2 instances are. So before the treatment, so please click on this and click on this button. So I'm going to move it to this side. Now see, before the treatment is already here. Now I need to fill up the blank cell. I'm going to select 8 weeks after the treatment. I'm going to move it to the other side. Now, automatically in Jamovi, it will give you paired sample t-test results. Now, this is before the treatments and after 8 weeks of treatments. This is a t-test. The t statistic is 15.6, degrees of freedom is 19. Why? Because we have 20 participants. And here's the significance. So this is pretty statistically significant. So pretty safe to say the CBT actually has effectiveness or has a significant effect in alleviating suicidal ideation because the scores seems to have come down. But now I need to just go ahead and observe some descriptives. So click on this descriptives button. See, before the treatment, the mean value is 35.5. And you can see there's a reduction of almost 15 points because after the 8 weeks, the score has come down to 20.3. And here I think you can go for mean difference as well. If you click on mean difference, you can see in the first table, the mean difference has appeared now, that is 15.3. And I'm going to just go ahead and do some normality testing as well to see whether this is normally distributed. Well, seems like they are all normally distributed. Nothing demonstrates any violation. But if not, there's another method that you can do. You can go to this exploration descriptives and then, select all the variables like this. And then here also you can go ahead and observe whether these things are normally distributed or not. Here you can select standard deviation, minimum, maximum, and then skewness, kurtosis, Shapiro-Wilk. All of these can be selected. And if I just go through and check here, well, it's slightly skewed, not heavily skewed. And in terms of kurtosis, I think kurtosis is pretty okay. It's just, I think, before the treatment, Shapiro-Wilk says it is violated. Not just for that, I think for most it says the same. I think apart from the after 6 weeks, everything else is pretty much violating. Yeah, I think 6 weeks, sorry, 4 weeks, 6 weeks, and 8 weeks. These are not violating because 0.05 is the threshold. So these two are slightly above it, and this one is also okay, but the others seem to pretty much violate. So what you can do is you can generate some plots here. Let's see whether we can get some histograms. These are our histograms before the treatment. So you can see this is slightly, not just slightly, I think it is skewed 2 weeks after the treatment, once again skewed. 4 weeks after the treatments, slightly skewed. 6 weeks, yeah, skewed. And this one seems to be a bit normal. So let's click on the density option as well to further observe this. Yeah, so it is a bit skewed. You see, this one is skewed as well. Yeah, all of these are skewed when you visually inspect. So in that case, you can't directly go with what you call the parametric option, but that's okay. Let's go back to paired t-test. I'm going to again rerun. Now I know that this is not normally distributed. So we selected the basic descriptives, and then I'm not going to select the normality test option here because for some reason it gives a different interpretation. You can go ahead and do normal testing separately like I just did. Main difference. So this is the basic information. Now, here you have the option to go with students t-test, or if not, you can go with Wilcoxon as well. So Wilcoxon one here would be the non-parametric version. And you can see still it is pretty significant. It is significant. So I'm going to get effect size as well. Let's see what exactly the effect size says. Now, coherence D for the independent, not the independent, paired sample t-test, the repeated measures t-test, that is 3.49. So a coherence D above 0.8 is a pretty larger effect size. So what is meant by this value is how much of a uh, difference the two groups have in terms of standard deviation units. So something like 3.49 is actually a pretty big difference. I don't think usually you would find this kind of significance or this kind of effect sizes, but this is just hypothetical data. That is why you exactly get a coherence D of this value. And then let's go with the Wilcoxon. Here you have effect size from biserial correlation, rank biserial correlation. So here what happens is this is a correlation for the two times here. So if you consider this two variables here before the treatment and after 8 weeks as A and B, or if you assign the values 1 and 2 for before the treatment and after the 8, and then if you correlate this 1 and 2 uh, with their respective scores, you can see there's a noticeable, what do you call, uh, relationship if you observe this in a scatter plot. Now, with the data, with the way that we have given data, you can't directly run it. But what you can do is you can enter the data slightly differently. For example, you can create one variable indicating whether it is before the treatment or after 8 weeks of treatment. For example, before the treatment would be 1, after 8 weeks would be 2. And then you create a second variable with the respective scores for each, and then you run a basic Pearson correlation. And then once you run it, it is not a Pearson correlation, it's a point biserial correlation. Why? Because whenever you have a variable with dichotomous options, which means a categorical variable and a continuous variable, that is going to be a point biserial correlation. So usually a value closer to 1 indicates that there is a stronger effect size. Now, the point biserial correlation is 1.0 here because you can see a steady relationship here. Now, I was earlier telling that from 1 to 2, how exactly the relationship is going to go. Now, in this case, it's a uh, you should be able to observe a clear reduction in every, from 1 to 2 you can see a clear reduction in the suicidal ideation. So here you have a rank biserial correlation of 1.0. it should technically be a negative score. I don't understand why exactly they are giving a positive score here, because there is going to be a negative relationship. But regardless of the direction of the correlation, because here our intention is not to find the correlation, but to get the strength of it. So the strength is 1.0, which indicates that there's a noticeable relationship, and the noticeable relationship is a perfect relationship. Therefore there is considerable effect size. So usually if this is closer to 0, probably you would notice the study is not significant. Now here the study is significant, and the rank biaxial correlation is also uh, perfect. So yeah, in that case, we can confirm this paired sample t-test is statistically significant using both the parametric and non-parametric. So since this study indicates violation of normality, I am going to go with Wilcoxon's output to interpret the study results. So that is exactly how you would run a paired sample t-test or a repeated measures t-test. Now that we have some understanding about normality, I'm not going to check normality again when I run ANOVA, but I'm going to go ahead and click on this ANOVA button to run repeated measures ANOVA. Now, if you haven't run ANOVA's repeated measures using Jamovi, this is not always understandable or comprehensive just by looking at how it is going to work. So here's how you are going to do this. Here, first you are going to define or identify your factors and the level. So I have just one factor, CBT. So I'm going to just write it here, CBT. My first level is before the treatments, and the second one is 2 weeks after the treatments, and then this one is 4 weeks after the treatments. This one is 6 weeks after the treatments, and this one is 8 weeks after the treatments. Now you can see when you add all of this, so I don't have level 6, I just have 5 levels for the same factor. Now they have created the required cells down below. So click on one of these before the treatment, and I'm going to just click on before the treatment on my left side, and then I'm going to click this transfer button here and transfer this data. Now, as we transfer the data, it will automatically do the analysis for us. Now, transfer the second week one to the second week cell. See, these cells are matched. I am matching the variables that I have with the levels on the right that I have created. So 4 weeks, 6 weeks, I'm going to transfer this as well. And then finally, 8 weeks. Okay, now I have transferred my data. I don't have between subject factors. So if you want to run probably a mixed factors design, you can do that as well here. And I don't have covariates, so I'm going to just keep it there. Now, before we go through these effect size calculations and all of that, I am going to go ahead and click on assumptions. Now, just like you have homogeneity of variances in uh, independent t-test or independent groups ANOVA, here you have something called the sphericity test. This is also just for us to see the differences in the variances in all the instances of measurement, whether they are equal or significantly different from one another. So I am going to just run the sphericity test. The sphericity test that you run in the repeated measures ANOVA is called Mauchley's test. I hope my pronunciation is correct. So this particular output should not be significant. If it is significant, what it indicates is a violation of sphericity. So now we don't have normality assumption, and at the same time we don't have what you call sphericity assumption as well. So when you don't have sphericity assumption met, there is a correction that you have to do. There's two options here. One is Greenhouse-Geisser, and the second one is Hunfeld. So you have to select one of these to go ahead and do this correction. Now, sphericity assumption is violated. So sphericity corrections, I'm going to declick this, and then I'm going to click on Greenhouse-Geisser. So Greenhouse-Geisser is usually done uh, to make a slight correction. And when I click on this, you can see here, they have added what do you call the sphericity correction here, Greenhouse-Geisser. And based on this, they have done a slight correction. So if you click on this none button, you will have your normal, the output as well. This is just repeated measures ANOVA. You can see here, without any corrections, without any sphericity corrections, you can see the degrees of freedom is 4 because you have 5 groups. So not 5 groups, 5 instances of measurement. So this is 4. And then here we have a larger F statistic. The larger the F statistic, the larger the significance is going to be always. And with the Greenhouse-Geisser or Greenhouse-Geisser correction, you can see the degrees of freedom is changed. So depending on the degrees of freedom, the final cutoff point changes. If you can go through the previous videos I have uploaded on step-by-step manual computations of ANOVA, you would know that degrees of freedom values are required to get the final cutoff point. So still, it is pretty significant. So here, Greenhouse-Geisser is a bit of a conservative approach. So you can click on Greenhouse-Geisser, but depending on your interest, you can go for this Hunfeld or any other one for that matter. But here in Jamovi, you get only these two options. But I'm going to go with this Greenhouse-Geisser or Greenhouse-Geisser. Now, there are some reasons that one has to consider when they go for these type of corrections. So usually the general understanding is that Greenhouse-Geisser correction, it adjusts the degrees of freedom for the F-test to account for the lack of sphericity. So our sphericity is violated. That's why we selected it. Like I mentioned, it's a conservative approach. So this actually reduces the risk of type 1 error. Now, you know type 1 error. Type 1 error is incorrectly rejecting the null hypothesis. So which means you are seeing a larger effect size. So, and at the same time, when there's a larger effect size like that and there's significance, sometimes it increases our chances of incorrectly rejecting our null hypothesis. So to reduce, that is type 1 error, so we are, since the likelihood of increasing, since the likelihood of type 1 error is increased here, what we do is by this correction, by this Greenhouse-Geisser, by this sphericity correction, we are reducing that likelihood of type 1 error. So that is exactly what we are doing here. So by the Greenhouse-Geisser correction, we are reducing the risk of type 1 error. So usually if you don't have more than 2 instances of measurement, you don't have to consider this. But if you have more than 2 instances of measurement, then in that case, yes, you have to go ahead and check for sphericity assumption. And after checking for sphericity assumption, if it is violated, then you have to go for a correction as well. Now, once again, I am going to go for effect size as well. You have generalized eta squared, and partial eta squared. Now, in a previous video, I have mentioned why eta squared and partial eta squared has to be considered and what's the difference between these. If you do a factorial ANOVA to consider each independence factor's impact or influence on the dependent variable, so to get that unique effect size for one of the independent variables, in that case, you have to go for partial eta squared. If not, in the instance where you have only one independent variable, you can just go with eta squared. Now, here's the eta squared. Eta squared is 0.594. So basically what it says is the independent variable accounts for about 59% of the variance in the dependent variable. So it's a pretty good effect size as well. So that's good work. And then you can go for post hoc tests. I'm going to select this, my independent variable. So I'm going to just translate to this other side, and then it will generate the post hoc test. And these are multiple combinations. And if you just check, all of these are statistically significant. All the combinations before the treatments with 2 weeks, before the treatment with 4 weeks, and then before the treatment with 6 weeks, 8 weeks, and 2 weeks with the rest, 4 weeks with the rest, and 6 weeks with 8 weeks. All of these are significant. So essentially, these are just a bunch of t-tests. So technically speaking, you don't need to run a repeated measures t-test. You can just go for the ANOVA itself. And if you have, of course, more than 2 groups, then it will give you the required results. So this is, we have done this through Takis, but you have other ones as well. So I'm not going to go for those. But yeah, this is pretty much what you need to do in repeated measures ANOVA. So you have a non-parametric version as well, that is Friedman. So I'm going to just run the Friedman here as well. Once again, I'm going to put all of this to the right side. And I'm going to go for descriptives. See, like we did in the previous one as well. Now, previous one, it was a parametric one, but we did a small correction. Here we did the sphericity correction, and then based on that, we interpreted our results. But here we can do the Friedman test, and using the Friedman test, we can once again interpret our findings. It is still pretty significant. You can still get the mean differences, and then you can get a descriptive plot here. You can see the, now here I have more content written. As a result, you can see the x axis here, the labels. But if you consider each of these points here as what you call before the treatment, this one is before the treatment, this one is 2 weeks, 4 weeks, 6 weeks, and 8 weeks, you can see the average tends to drop down very clearly. So that's good. I'm going to just declick on this, don't need it. And then pairwise comparisons, once again, everything is pretty significant. So based on how you are viewing this, you can go with the repeated measures ANOVA non-parametric for this, and then interpret this. Or if not, if you think the normality violations are not too big, maybe then you can go ahead with the repeated measures ANOVA. But since the sphericity assumption is violated, you can go with the sphericity correction and then interpret your results. So this is it. This is exactly how you would do your study, and then you can report this in the APA format. So yeah, this is pretty much what I wanted to show all of you today. So now you have an understanding about what we have done in this study. So we have basically done a repeated measures t-test and repeated measures ANOVA, and we also did both parametric and non-parametric. So if you have any questions about this, feel free to drop a comment, or feel free to write about it wherever, the platform that I upload this video, and then I will get back to you with the clarifications required. So watch this video and let me know if you have any questions. So thank you very much for taking the time out of your schedules to go through my video. And I hope now you have a thorough understanding about how to use Jamovi to analyze a data set like this. So thank you very much, and I shall see you with a similar video again in the future.